Hello, chemistry students, and I hope you're having a good break. I'd make some comment about the weather or whatever, but I recorded this video before we left, so I have no idea what's going on. I wanted to put together a short video that hopefully you can watch toward the end of break just to refresh your memory on what we were talking about before break. We're going to pick up right where we left off when you get back, talking about interparticle forces, the behaviors of solids, liquids, and gases, and introducing chemistry math that will carry over into the next unit on equation stoichiometry. So we were talking about inter versus intraparticle forces, and on the screen here you can see a little diagram similar to what we had on one of our handouts, that inter means between and intra means within. So our analogy was the internet that connects from one location to another versus the intranet, which is the network within our building here at BTA. And you see the diagram here that shows the intramolecular attraction between hydrogen and chlorine in hydrochloric acid, and then the intermolecular attraction that occurs from one unit of hydrochloric acid to another. The physical properties of a substance such as density, viscosity, and state are related to these interparticle attractions. And really they're related to how effective those interparticle attractions are at controlling the physical structure of a substance. The nature of that interparticle attraction is caused by the particular electron structure of the substance, meaning it's controlled by the intraparticle bonds, the bonds that actually hold the substance together. Whether they're ionic, polar covalent, covalent, the shapes of the molecules, all of that relate to the nature of the interparticle attractions. Hopefully you'll remember that I gave you a handout at one point in class that showed the four main interparticle forces rated from strongest to weakest. We had the ionic bond, then the dipole-dipole attractions, such as in the water molecule, in particular hydrogen bonding, which is a special type of dipole-dipole attraction, and then the London dispersion forces under the overall umbrella of van der Waals forces that are fairly weak in terms of their effects in physical properties of substances. The overall effect of interparticle attraction is that it really dictates why substances are particular states of matter under specific conditions. So if the interparticle attraction is able to effectively control particle structure, then it's a solid. If the interparticle attraction can keep things together but not in fixed positions, it'll be a liquid. And if the interparticle attraction can no longer effectively keep the particles connected together, it's a gas. Remember, the interparticle attraction does not change, just how effective the interparticle attraction is at controlling particle structure, that changes. So anything that affects the ability of the particles to stay together, such as pressure or temperature, that will affect the state of matter. And remember that when we talk about state, we had phase diagrams. We looked at carbon dioxide and how under specific conditions of temperature and pressure, it could be a solid or a liquid or a gas. It may melt, it may condense, or it may undergo sublimation like dry ice does at room temperature and pressure. What affects the particles? Well, it relates to energy. We looked at how we break down the free energy of a system as temperature, which is the average kinetic energy of the particles in a system, also simply called their motion. We had enthalpy in the particle structure, and then we also have entropy, which is the amount of particle disorder. And in general, natural systems tend to want to move from a state of order to disorder. This showed up in the melting and freezing labs. You saw some temperature profiles that look a lot like these. And we saw the plateaus. In this case, it was a substance that was melting and freezing at 80.2 degrees Celsius. It's fairly similar to the naphthalene that some of the groups had. In this case, the plateau occurs because at that time, instead of changing particle motion, the substance at that particular temperature has to undergo a restructuring, and that restructuring is a change in enthalpy. So instead of the particles slowing down or speeding up, the particles restructure themselves. So at that time, even though it's heating and cooling, we don't see the temperature change because that movement of energy is coming out of particle structure and not particle motion. Summarizing it up, we had the main theories and laws that govern all of this. We had kinetic theory, and in your notes you had a little list of things that kinetic theory talked about. All matter is made of particles. Those particles are in constant motion, even all the way down to 0 Kelvin, absolute zero. At absolute zero, the particles can't be reduced in energy anymore, but that doesn't necessarily mean they have stopped. The interparticle attractions and the energy of the system control the physical behaviors. Also governing the movement of energy is the first law of thermodynamics, which essentially is the law of conservation of energy, and the second law of thermodynamics, which says that heat flows downhill. It always flows from high temperature to low temperature. Even though a cube of ice has a lot of internal energy, that ice cannot make a cup of coffee hotter. Energy will only move from the coffee to the ice and not the other way around. When you get back, we will get back to working with gases. Remember, we defined ideal gases, and we said that there is really no such thing as a perfectly ideal gas. Under normal conditions, however, most gases are approximately ideal. They're close enough to ideal in order for us to use the ideal gas law, PV equals nRT. So the relationship of pressure, volume, number of moles, and temperature through the ideal gas constant R. We also will talk about some rounding rules and some unit conversions. We brought those up the last day of class before break. There is a unit conversions video that if you have not watched it yet, you probably should go through that as we convert through various metric units like milliliters to liters and milligrams to grams. You also have the little bit of PivNert practice that we had on the last day as well to finish up over break. Hopefully this video refreshes your brain a little bit on the major topics that we were talking about. Tried not to make it too long for you, but we're going to pick up right there when we get back, and hopefully by the time we get back, Boston will look more like this. I'm not going to hold my breath, but spring should be coming, hopefully coming. The groundhog said it was coming. Of course, the groundhog's usually not right, but there is a little bonus opportunity down here at the bottom of the screen. Send me an email with the word review in the subject line by the end of the day, Sunday the 24th, and I'll throw an extra credit point your way just for taking the time out of your break to do a little bit of chemistry review. Hopefully everything's going great, and I will see you when we get back.